Today we tackle one of physics' deepest mysteries, how quantum entanglement instantaneous correlations coexist with Einstein's speed of light limit. Two particles connected by quantum entanglement seem to communicate instantly across any distance, yet Einstein's relativity forbids anything from traveling faster than light. Let's start by understanding what quantum entanglement actually is, and why it seems so strange. When two quantum particles become entangled, measuring a property of one particle instantly determines the corresponding property of the other, no matter how far apart they are. If we measure the first particle and find it spinning up, the second particle instantly becomes spin down, even if they're separated by galaxies. The correlation between these measurements is perfect, occurring with no time delay whatsoever, which seems to violate the cosmic speed limit. Now let's examine Einstein's fundamental principle, that nothing can travel faster than light. The speed of light c equals 299,792,458 meters per second, approximately 300,000 kilometers per second. Einstein's special relativity theory absolutely forbids any information or influence from traveling faster than this speed limit. Anything moving faster than light would violate causality itself, allowing effects to precede their causes and creating impossible time paradoxes. If velocity v exceeds c, then the very foundation of cause and effect would collapse, making physics meaningless. So here's our puzzle. Doesn't quantum entanglement with its instantaneous correlations directly violate Einstein's sacred speed limit? In 1935, Einstein-Podolsky-Rosen formulated this problem as the famous EPR paradox. Einstein, Podolsky, and Rosen argued that quantum mechanics must be incomplete, because the alternative seemed to be spooky action at a distance. Their logic was simple. Either quantum mechanics doesn't tell the whole story and there are hidden variables, or particles really do influence each other instantaneously across space. Einstein famously called this phenomenon spooky action at a distance, refusing to believe nature could work this way. In 1964, John Bell discovered a mathematical way to test whether Einstein was right about hidden variables. Bell's inequality states that the absolute difference between correlations P of AB and P of AC must be less than or equal to 1 plus P of BC. If Einstein was right and hidden local variables determine measurement outcomes, then correlations between measurements must satisfy this mathematical constraint. But quantum mechanics predicts violations of this inequality, meaning nature doesn't use hidden local variables at all. This graph shows quantum mechanics in blue predicting a smooth cosine curve, while local hidden variable theories in yellow predict a linear relationship that never exceeds certain bounds. Since the 1970s, experiments have consistently confirmed quantum mechanics and violated Bell's inequality. Alain Aspect's groundbreaking experiments in 1982 definitively showed that nature violates Bell's inequality, ruling out local hidden variables. Modern experiments measure the Bell parameter S as 2.697 plus or minus 0.015, while local theories require S to be less than or equal to 2. The observed violations exceed local theory predictions by more than 175 standard deviations, making the result absolutely certain. Experiments decisively favor quantum mechanics over local hidden variable theories, confirming that entanglement is genuinely non-local. This raises our central question again. If entanglement is real and non-local, how does it coexist with Einstein's prohibition on faster-than-light signaling? The resolution lies in a subtle but crucial distinction between correlation and communication. While entangled particles exhibit perfect correlations, these correlations cannot be used to send messages or transmit any controllable information. The key is that individual measurement outcomes are completely random. Only when compared do the correlations become apparent. When Alice measures her particle, she gets random outcomes with 50-50 probability, and the same is true for Bob on his end. Only after they bring their results together, using conventional slower-than-light communication, do they discover the perfect anti-correlation. This is the crucial insight. Correlation does not equal communication, and only communication is forbidden from exceeding light speed. The no-signaling theorem proves mathematically that entanglement cannot be used for faster-than-light communication. The reduced density matrix ρA, obtained by tracing out system B from the joint state ρAB, shows that Alice's local measurements are independent of Bob's choices. No matter what measurement Bob chooses to perform, the statistics of Alice's results remain unchanged, preventing any information transfer. The probability PA of outcome A given Alice's setting A equals the probability given both settings A and B and Bob's outcome B. This diagram shows that even though particles are entangled, the quantum barrier prevents using this connection to send controllable signals. Another aspect of the resolution involves understanding how different observers view the measurement process. Due to relativity of simultaneity, different observers moving at different speeds will disagree about which measurement happened first. In one reference frame, Alice's measurement might occur first, while in another frame moving relative to the first, Bob's measurement occurs first. Crucially, despite this relativity of simultaneity, no reference frame can exploit entanglement to send information into its own past. Causality is preserved in all reference frames because the no signaling constraint holds regardless of the spacetime foliation. Let's work through a concrete numerical example to see how the correlations work without signaling. Consider a singlet state. Psi equals 1 over root 2 times up, down, minus down, up, a maximally entangled state. When Alice measures spin along the z-axis, she gets spin up 50% of the time and spin down 50% of the time, completely random. Probability of Alice measuring up equals 1/2. Probability of down also equals 1/2. Similarly, Bob measuring along the z-axis also gets 50-50 random results, seeing nothing unusual. However, when Alice and Bob later compare their results, they discover perfect anti-correlation. Whenever Alice measured up, Bob measured down, and vice versa. The joint probability of Alice up and Bob down is 1/2, and Alice down with Bob up is also 1/2, with 0 probability for same results. This visualization shows both Alice and Bob seeing random 50-50 distributions, yet their individual results are perfectly opposite when compared. The quantum correlations become even more interesting when Alice and Bob measure along different angles. The correlation function E of theta equals negative cosine of theta, where theta is the angle between their measurement directions. At 0 degrees, measuring along the same axis, the correlation equals -1, showing perfect anti-correlation. At 90 degrees, perpendicular measurements, the correlation drops to 0, and their results become completely uncorrelated. At 180 degrees, opposite directions, the correlation equals +1, giving perfect correlation instead of anti-correlation. This curve beautifully demonstrates how quantum correlations vary smoothly with measurement angle, following the cosine function. Despite these angle-dependent correlations revealing quantum mechanics predictions, no choice of angles allows actual information transfer. Understanding this paradox's resolution has profound implications for physics and our view of reality. We learned that reality is fundamentally non-local, with instantaneous correlations across space, yet causality and the light speed limit remain inviolable. Modern quantum information science exploits these non-local correlations for quantum cryptography, quantum computing, and quantum teleportation. These principles enable quantum networks that can perform tasks impossible with classical physics, from unhackable communication to exponentially faster computation. Most fundamentally, this resolution challenges our classical intuitions about the nature of space, separability, and the relationship between events. Modern experiments continue to test and verify these principles with increasing precision. China's Mikias satellite has demonstrated quantum entanglement over 1,200 kilometers, proving these effects work at cosmic scales. At 1,200 kilometer separation, light takes 4 milliseconds to travel between the particles, yet correlations appear instantaneous. Recent loophole-free Bell tests have closed every possible classical loophole, definitively confirming quantum non-locality beyond any doubt. This shows how satellite experiments distribute entangled photons to multiple ground stations, testing quantum non-locality across continental distances. Researchers worldwide are now building quantum internet prototypes that exploit these correlations for secure communication networks. Let's synthesize how quantum mechanics and relativity peacefully coexist despite initial appearances. Quantum entanglement is absolutely real, creating genuine, non-local correlations that transcend spatial separation. Yet the randomness of individual measurement outcomes prevents these correlations from transmitting any controllable information. Einstein's relativity remains perfectly intact, with causality preserved and the light speed limit never violated. The combination of quantum non-locality plus the no-signaling theorem equals perfect consistency with relativity. Quantum mechanics and special relativity, far from contradicting each other, form a beautifully consistent picture of reality where both are simultaneously true. The universe turns out to be stranger than we imagined, with non-local quantum correlations pervading reality, yet everything remains mathematically consistent and causally coherent. Perhaps the deepest lesson is that physical reality doesn't owe us classical intuitions, it follows mathematical principles that transcend our everyday experience.